Okay, let us now proceed to part 6, the Mathematica simulations. So we have the simulations of the Rodrigues formula here, this formula. So for n equal to 0 here, so we just substitute the n equal to 0 here. So p1 of x is equal to 1, and for order 1 here, so we have the corresponding uh, plot here for p1 of x here. Then we have the p2 of x. This is the p2 of x here. We have the p3 of x. We have the complete simulation here from 0 to 10. Okay. So slider controls the degree n here, computes pn of x directly from Rodrigues formula, then plots it on -1 to +1. Now we have the Rodrigues formula and the Legendre polynomials here. For example, here, so it shows that the Rodrigues formula exactly matches the Mathematica Legendre polynomial here. So this is from -1 to +1. So we have the colored red here is the Rodrigues formula. It's according to Rodrigues formula. We have the Legendre polynomial for the dash curve here. So it shows that the Rodrigues formula exactly matches Mathematica's Legendre. Here we have the here, for example, the next step, plotting here, manipulate. So for example, the blue here is equal to 0. So if this is equal to 0, so this is equal to 1. So y equal to 1 here at corresponding value for the Rodrigues formula. And we have the 1 here. So this is equal to 1. So x squared minus 1. So the plot of that is given by this color blue. Then we have the derivative of x squared minus 1. So that's equal to 2x. That is equal to 2. So we have here 2. And we have also here n equals to 3 here. So the third x squared minus 1 raised to the third. So we have the plot here from -1 to +1. The derivative of x squared minus 1 raised to the third is given by this curve. The plot of this is equal to the second derivative of x squared minus 1 raised to the third. For example, we have fourth here. So x squared to the x squared minus 1 raised to the fourth. So we have the plot of this. Then the second derivative of x squared minus 1 raised to the fourth is given by this orange color. Okay. So the first slider here is refers to the power n. The second slider here is number of derivatives k here. When k equal to 1, we obtain the normalized Legendre polynomials. To make them normalized, define the p bar of x equal to the square root of 2n plus 1 over 2 times the Rodrigues formula here. Now we have the integral from -1 to 1, then equate this equal to 0. So the square of the p bar of x dx. Then Mathematica simulation of Rodrigues rotation formula. So we have to first remember that the blue arrow here is the original vector. We have the red arrow here, the rotated vector, and the black arrow here is the rotation axis k. So slider theta here continuously rotates the vector. So axis vector here is automatically normalized. So for example, here we have this color. This is the axis of rotation. Then we have the given vector here, vector v, vector. This is the rotated vector. For example, we adjust the angle here, and can also adjust the x component of the vector, the given vector, and so this is the given vector. Here is the color blue. The rotated vector is the red vector here, and we have the axis of rotations. This color black. So why this is physically important? So this is the rigid body constellation, angular momentum transformations, spacecraft attitude control. So these are some of the applications. We have the robotics and 3D kinematics and continuum mechanics. The mathematical simulation of Hermite polynomials. So this we have here the Hermite polynomial. For example, n equal to 3 here, and if n equal to 4, n equal to 6 here. So we just substitute here for n equal to 0, n equal to 1, n equal to 2. So we just substitute here. So we have the corresponding value of the order of h as a function of x here. So for example here, n equal to 8. So we have this. So shape and oscillation increase with order n, orthogonal and polynomial structures. For example, we have the inner product here from A to B. So the inner product here is PM and PM equal to 0 for m not equal to n. If m is equal to n, so this is equal to 1. So Hermite polynomial with Gaussian weight here. So we have the factor here, the e to the negative x squared multiplied with the Hermite polynomial here. So we have the product here. For example, n equal to 2, 1, so n equal to 4. So we have the corresponding plot here. If n equal to 5, n equal to 60. So we have the simulation from 0 to 10. So we have the advanced compare multiple Hermite orders here. For example, if n equal to 1, so this is the plot. If n equal to 0, so the corresponding Hermite polynomial here, the value is equal to 1. If n equal to 1 here, so this is equal to, so we have the h sub 0 here is the horizontal axis, and we have this if n equal to 1 here, so that's equal to 2x. By substitution here, n equal to 1 as a function of x, so this is equal to 2x. So this is equal to 2x here. This one equal to 2x. So this is for h sub 0 here. For n equal to 2, so for example, n equal to 2 here. So we have the parabola here. So this is equal to n equal to 2. And this is 1. This is for n equal to 1 here. So n equal to 2. So n equal to 0 here. So for n equal to 2, so we have the parabola here. For n equal to 3, we have the corresponding plot here. Okay, so let's see the n equal to 3 here. So this is for n equal to 3. And this is for n equal to 2. So this is for n equal to 2. So n equal to 3 here by graph. So this is for n equal to 3. This one. So let's proceed to Laguerre's polynomial mathematical simulation. So we have the definition of Laguerre's Laguerre polynomial here. So this one. So for n equal to Laguerre's polynomial here from uh, this is from this one from 0 to 5 here. So n equal to 0, and this is for n equal to 1, n equal to 2, this is n equal to 3. Now this is for n equal to 4 here, and this is for n equal to 5. So if we plot them, so we have this Laguerre polynomial. The plot of all this, if n equal to 1 here, so L equal to 0 here equal to 1, so L equal to 0, so this is equal to 1 here. For L equal to 1, so 1 minus x, so this is for L equal to 1 here. Now for L equal to 2, we have this. For L equal to 3, we have this. We have this for L equal to 3. For L equal to 4, we have this also. For L equal to 5, we have this. Okay, so for the different values of n here, we have the simulation for different values of n. For different values of n here, from 0 to 10, we have also this. Now this is for the uh, Laguerre with the parameter here. So parameter A here, we have the degree 4. So in our example, we have this is the degree 3, and the corresponding value for the parameter here is equal to 0. The parameter here is equal to 0, and the degree is equal to 3. But we can also change the value of n here. For example, here is equal to uh, uh, for example, degree is equal to 4 here, and we can change the value parameter here. For example, change the value parameter. This is equal to 2. Example, parameter is equal to 1.5 here. So we have the degree equal to 4. So the degree is refers to the highest exponent of the polynomial. So we have the 3D plot here. So we have a parameter equal to 0 here. So this is for the fourth degree. So x to the fourth is the fourth degree. X to the fourth, the same degree here, fourth degree. But the parameter here is varied from 0 to here. So if the parameter is equal to 2, we have the same degree here, 4. So we have here in this plot, this is the plus 3D here. So from -2 to +3. These are the values of the parameter. The value of x here is from 0 to 10. Then uh, if we vary from negative to 3, uh, if we change the value of if we have the different values of the parameter here, so we have the different values of the fourth degree Laguerre polynomial as a function of x and parameter here.